Okay, great. You are pretty far into geometry now. We almost finished the straight line geometry laws. This is the last of the 3 straight line geometry laws, so well done. Okay, so we're looking today at angles around a point, and this law basically says that the angles around a point add up to 360 degrees. So this means that if you add all the angles that form a full revolution, you'll get 360 degrees. Now you know this, right? If I take an angle, okay, or if I take a, better way to do this. Yeah, okay, so let's say I have 2 lines, right? I've got a line and I've got another line, and I keep opening up that second line, and I keep opening it up and opening it up and opening it up until it's all the way over here, and eventually it's all the way back where it started, right? So that I've got my angle that goes from here all the way around to there. We know that that's called a revolution, right? And that is 360 degrees from there all the way around to there again. So what that means is if I take this full revolution and I split it up into a number of angles, let's say these 1, 2, 3, 4 angles, then these 4 angles added together should give us 360, right? It's the same logic as the angles on a straight line one. If you take something 360 degrees and you break it into parts, then the sum of those parts should still give us 360 degrees. So if we put another angle here, then those 5 angles added together should give us 360 degrees. Very important that you have all 5 of them though. Okay, if we didn't know anything about this angle, then we couldn't use the fact that the angles around a point equal 360. Okay, now just like with all geometry, we need a reason. And our reason here, please be very careful. You might see in some old textbooks that the reason revolution is acceptable. That's not the case anymore. Okay, the curriculum has changed. They've changed the reason. So please do not use revolution if you see it. The correct reason to use is angles round a point. Okay. This is the correct reason to use now. Angles round a point, not revolution. Got it? Okay, and yeah, that's all there is to this law. So I'll do a few examples with you, just like usual, and then I'm going to set you free, and you're going to try this. And then I think tomorrow or the next day, you're going to try a worksheet with them all together, all 3 of these laws together. And then you're finished with straight line geometry. Okay, guys, so here's our first example. They want us to determine the size of x. Here is our diagram. Now let's quickly go through our little toolbox of straight line geometry rules. We know that angles on a straight line add up to 180. I don't have a straight line here though, right? A straight line means a line that goes through the point where all the angles are and carries on through the other side. We also can't use vertically opposite angles because we don't have that cross shape anyway. So the only option we have to use is angles around a point. Now let's check if we can use angles around a point. Do we know all the angles? Okay, if I were to start here and go all the way around and end up back where I started, I have x, that's what I'm looking for. I have 150, I have 140. Perfect. This 360 has been split into 3 angles, and I've got all 3 of them. Okay, so we set up our equation with a reason, and then we solve the equation, same as usual. Okay, so we're setting up our equation. So x plus that 150 degrees plus that 140 degrees all together need to add up to 360 degrees because all together they make up a revolution. Okay, and our reason, angles around a point. Okay, now we solve for x. So we're going to keep x here on the left. We're going to subtract 150 and 140. Okay, so we've got that equals to 360 degrees minus 150 degrees minus 140 degrees. And when we simplify both sides, we get that x is equal to 70 degrees. Okay, so this would be a 3-mark question. Most of these geometry questions are 3 marks. 1 for setting up your equation, 1 for your reason, and 1 for your answer. Okay. Okay, so I'm going to pause you there, put up the second example. Okay guys, so here is example 2. We need to determine the size of x. Now we've got a lot of x's in this diagram. All of the x's will have the same value. They'll have the value of whatever x is. And if we look at this, I'm hoping you guys can see the first thing you do, you pick up a highlighter. If you see that cross shape, that shape that means vertically opposite angles, you highlight it, hey? So I see that cross shape from S to P and from R to N, I have two straight lines. Okay, maybe we'll use them, maybe we won't, but it is important. Okay, then we need to determine the size of X. So I'm actually seeing on second look at this question that you could actually very easily do it by just ignoring the bottom half of the diagram and saying that X, 90, and 45 are angles on a straight line. Okay, so you could do it that way, but that's not the way. It would be perfectly acceptable if you did it that way, but I want to show you the other way because it's the other thing that I'm trying to do an example of is the other method. Okay, so using the other method, the angles around a point, because that's what we're doing here, we would have to start at the line and go all the way around to end up back at the same line, right? And add all those angles together to add up to 360. Now let's see, we would be going that angle, that angle, that angle, that angle, that angle, and this angle, all added together equal 360. But the problem is I don't know this angle, so how am I going to add it in my equation? Well, luckily I took my highlighter and I highlighted that cross shape, because we can then see that this 45 and this unknown angle must be equal, right? Which means this must be 45 degrees. Perfect. But in geometry, you never skip steps. Okay, I know in normal maths, occasionally it's okay for you to think, I know 4 divided by 2 is 2, so I'm just going to skip me showing that working out. Normally that's fine. But in geometry, every single thing you think, you need to write down. Okay, so I'm going to show you now how we would set that up. Okay, so the plan is to use angles around a point. But before we can do that, we need to know what this angle is. To find this angle, we can say it's equal to that because they're vertically opposite. But this angle doesn't have a letter attached to it. So we need to remember back to the first lesson of geometry. How do we name an angle? We name it according to the lines that form it, hey? So this unknown angle here is called angle SOR with a copy on the O, okay? Angle SOR. And angle SOR is equal to 45 degrees. And I know that because it's vertically opposite this 45 degrees. Okay, so we put our reason, vert, op, angles. Okay, now that we know this is 45 degrees, now we can go and do angles around a point. Okay, so now we can say that X plus that 90, remember the little blocky, means 90 degrees here. So it's X plus 90 plus 45 degrees plus 2x plus another x plus this new 45 that I've just found out. All of those added together give me 360 degrees. I know this because they are angles around a point. Okay, now we solve for x. Oh my word, okay. So on the left, I'm keeping my x's. So I've got x plus 2x plus x. Okay, on the right, I need all my contacts. So wait a minute. Constants, sorry. I want all my constants on the right. So the 90, the 45, the 45, I need to subtract. 90, 45, 45. Okay, we simplify both sides. So on the left, I've got 4x, right? Yeah. X plus 2x plus x is 4x. On the right, I've got, what's that, 270, 180. And as usual, the last step when you're solving an equation is you divide by the coefficient of x. And when we divide both sides by 4, 180 divided by 4 is 45 degrees. Okay, and that's it. We've solved it. Again, really nasty one. Much more likely you'd only see something like this in grade 9. But yeah, there you go. If you can do the tricky ones, then the easy ones are a breeze. So let's rather focus on the tricky ones. Okay, that's it. So you guys are going to do that worksheet on angles around a point. And then tomorrow you're going to do a revision exercise on all of the straight line geometry thus far.